hunter?
Yeah, I'm here.
Senior hunter. You have to go see him about a test or something. Just right.
Yeah, I know where senior hunters at.
Senior hunter.
Right now.
Yep.
That is some of the best gringo Spanish I've heard you speak.
Things right in Spanish, I'm like,
He was in my Spanish class in like 9th grade.
I don't even try and speak in other languages because I can't so bad at it.
yeah. It's because my best friend, she's like, Chipotle. She's always wrong. I can't. It's a problem. But she doesn't know. How are you supposed to say it?
Chipotle, isn't it?
Okay, because my sister and I were arguing about that. I thought it was Chipotle, but she thought it was Chipotle.
Okay. So now that our conversation on Chipotle has been recorded, we are going to talk about antiderivatives today of polynomials and antiderivatives of some of our trig functions. So if you look at the bottom, or you, like I said, you can rewrite it and put it in your notes. We're going to graph the following and find the exact area from 0 to 1. Then we're going to find the exact area from 0 to 2, exact area from 0 to 3, 0 to 4. We could keep going. We're going to graph the answers on the coordinate system and use them to find the equation of the antiderivative. Because we've already established that finding area under the curve gives us, it was the opposite of differentiation. So, if we look at this function, our first function is f of x equals 2. What will that function look like on the coordinate system if we graph this function itself? F of x equals 2 look like? Straight horizontal line. At 2. So I'm going to graph my line in one color and graph the answers we get in a different color. Just any other color, so it doesn't look like we're doing the same thing. So first I've asked you to find the area under the curve from 0 to 1. So if we start at 0, go up to our function, and at 1, go up to our function, what shape do we have? Rectangle. Okay. And we know how to find the area of this shape. How do I find area of that shape? Base times height, length times width. Different ways to say it, but same thing. So what's the area of this rectangle? 2. So if we were to take our areas and make them into a function, that means we would actually have the coordinate 1, 2, because we traveled from 0 to 1, we ended at 1, and we had an area of 2. So this is where we ended. This was the area. So we have a coordinate, and to make a function, we start by plotting some coordinates. So our first coordinate we would plot is 1, 2. So that's why I did a different color, so that I could see, or you could draw 2 separate coordinate systems, whatever way you want. So now let's add a little bit more area. Let's go a little bit further. Instead of from 0 to 1, let's go from 0 to 2. Well, we've already considered this area, so I just need to add this extra area. How much more area do we have? 2 more. So what's our total area from 0 to 2? 4. Okay, so our next coordinate would be 2, 4. we're coming up with a function. We call this accumulating area. We started with a little bit of area, we added a little bit more. Now we're going to add a little bit more. How much more would we add? Two more. Okay. I picked a line specifically because we can actually find the area. We could do this in a more complicated manner, but we don't know how to find the area when it's curvy. So 2 more, that means my next coordinate is 3, 6. So many different colors today. Did everyone get the words written down? I was waiting to scroll down before everyone got all the... Okay. And I'm going to scroll down so it's easier to see. Okay, so let's do one more point. How much more area? 2 more. So I think we have enough points to establish a pattern. 4, 8. So what type of function does it look like we are forming by doing this accumulation of area? A line. Okay. So it looks like we are forming a line. I'm going to cheat. Looks like we formed a line. Specifically, what would the equation of this line be? We could use the 2 points, any 2 points, to find the equation. Or, if we know the y-intercept and we know the slope, we can just write the equation that way. What would the equation of this line be? Y equals 2x. Okay, so we've done it for one function. I want you to do it for this second function. This time we have the line. Let's see. That's where I can choose the color. Do green. We have the line y equals x. And I'm going to have to... There we go. We have the line y equals x. So this time our area under the curve isn't going to be rectangles anymore. What area will we have to find? Triangle for the first one, trapezoids after that. Or you could find the area of the square plus the area of the triangle on top. Okay. So I want you to do the same thing. Find the area from 0 to 1, then plot the point you get. Find the area from 0 to 2, plot the point you get. 0 to 3, plot the point. 0 to 4, plot the point. Okay, what points did you get for your area function? So if I start at 0, what's my area from 0 to 0? 0. So I've been kind of skipping that point, but really there's a point at 0, 0, 1 and 0.5, 2 and 2, 3 and 4.5, and 4 and 8. So I asked you to make a conjecture. What shape do you think this is? Parabola. So what do you think the equation of the function is? We know what's the basic parabola, x squared, and that's centered in the middle. This is centered in the middle, but the basic parabola you would go up 1 over 1, up 4 over 2, up 9 over 3, And this doesn't do that. Okay. Josh made a conjecture. He said, I think it's 1/2. Does that work? If we, instead of going up 1 over 1, up 1 over 1/2, instead of up 4 over 2, we only go up halfway, up 2 over 2.
And if you took the derivative of it, it would be y equals x.
Okay. So then he made a second conjecture. What would happen if I find y prime of this function?
It'd be X.
It would be x. What about the other one? What if I took the derivative of this function?
It'd be 2.
It'd be 2. So what have we discovered here? Okay. Anti-derivatives. So derivatives, we built a derivative by taking slopes everywhere. We build an antiderivative by doing this area accumulation, by adding up all the areas together. So 2x is the antiderivative, no, yes, 2x is the antiderivative of 2.
I'm sorry.
And 1/2 x squared is the antiderivative, or integral again. Antiderivative they usually use when we're doing just the equation for it. Integral usually more often they do when we're working with the graph, but they're basically the same thing. X. So I could have stated this another way. I could have said, take the integral of x, and what would we say? Here's our new notation. This is saying take the antiderivative. So if I said take the antiderivative of x, what did we find that to be?
1/2 X squared.
1/2 x squared. We did that graphically. So now we have a general idea of what the antiderivative is going to be. But we need a couple of details that we don't have yet. First of all, these are a lot more complicated opposites. Plus and minus, easy opposite. You know it's going to cancel immediately. This, we might need some other information. So we're going to look for some other patterns besides this. So, thus, integration is the opposite of differentiation. Good to know they are opposites. Differentiation. With differentiation, we say difference quotient because we're doing subtraction divided by subtraction. With integration, we say it's the addition, so the sums of multiplication. So they are opposites, but they are pretty complicated opposites. We need some more information because it's not exactly, this will not be our full answer yet. So we're going to look for another pattern. I want you to find the derivatives of these three functions. Go. Find the derivatives of these three functions. Let's So what are we noticing about the derivatives of these three functions? They're all the same. Every time I take the derivative, that constant disappears. So if I'm trying to go backwards, how do I know which constant to use? We basically don't. I heard Stephania say we don't. At least I think that's what she said. I'm going to assume. Okay, we don't know what constant to use unless they gave us more information. But we're not even going to work with trying to find the constant today. We're going to say we don't know. So what do we give something when we don't know what it is? We know it's a number, though.
B.
A variable. So we could use any variable, really, but they do use a standard variable when this situation comes up. So we said we knew the integral of x. Oh, I forgot one piece of our notation. We should say x dx. Just like when we did Leibniz notation and said dy dx, saying take the derivative with respect to x. This is saying take the integral and treat x as your variable. It's just telling you to integrate x and not some other variable. So we need to include that dx. We said it's 1/2 x squared. And now we know it has some constant. We don't know what that constant is. So we're going to give that constant a name. And they usually use a capital C for constant. So we can find this because we went through and did that graphical process. What if I want to make this quicker? I don't want to have to do a graph every time and figure out what my function is. So we need to find a pattern so that we could get from here to here with a formula instead of a graph. So let's go back to differentiation. And we know the power rule. If we're taking the derivative of x to the n, let's say cx to the n, because we could have a little constant in front, so lowercase c. Integration has the uppercase c, but here we're just saying some random constant. Then, how did we do our power rule? What was it? If I said, because you've used it already today, I said x cubed. How did you get from x cubed to 3x squared?
Times n by a constant.
Times n by the constant.
And then n minus 1.
We need to do this process backwards. So, if I want to integrate cx to the n dx, I want to go backwards. How would I get from n minus 1 back to n? Add 1, plus 1. So we know we're going to end up doing n plus 1. So then we had to multiply by n here. How would we get rid of it? Divide by n, but since we're doing this, since this is where we're starting and we went to n plus 1, we need to divide by the same as the exponent. We multiplied by the exponent here. We need to divide by the exponent.
Divide by n plus 1.
And we could write this two ways. You could either write just divide the constant, or you could write cx to the n plus 1 all over n plus 1. It's the same thing, because c and n plus 1 are just numbers. It's the exact same thing, just I usually like to make the fraction go out front, or you could make the entire expression fraction. Up to you. So there's our anti-power rule. We can also do some of our trig integrals pretty easily. Since we know it's opposite, if I know the derivative of sine is cosine, then I can do this backwards. I know the integral of cosine is what?
Sine.
Sine plus c. So any trig derivative we know, we can do the opposite. I could find the integral of sine, so the derivative of cosine is negative sine, so what would the integral of sine be if we're going backwards? The derivative of, let's write it out so we don't have to visualize it,
Would it be negative cosine?
cosine, yes it would be, is negative sine, and I integrate positive sine, then the negative can't just disappear. But again, since we're going in the opposite direction, it'd be negative cosine. Or what are some other trig derivatives we know? Just the basic, not the inverse. What else do we know?
Tangent.
Okay. Tangent equals secant squared. So the derivative of tangent is secant squared. So what do we know the integral of?
Secant squared.
The integral of secant squared is tangent. We take the answer, integrate it, we get back to what we were starting with. So we need to make a whole bunch of more note cards, because now we have a lot of integration formulas. And I liked having the constant in front. Okay, so we've done all the build-up, so hopefully we understand where these formulas came from. But now we're just going to do the practice. Find the antiderivative again. I could have said integral. And there's actually two types of integrals, an indefinite integral and a definite integral. We are currently working with indefinite integrals. And we will explain the difference later on.
Works for me.
So we are finding the antiderivative using which rule? Anti-power rule. So right now the only thing we can integrate is those 6 specific trig functions and a polynomial that has anti-power rule that we can apply to it. We cannot integrate multiplication, division, chains. We can only do polynomials right now. Just like when we started derivatives, we can only differentiate polynomials. So we do the antiderivative. That said, we need to add 1, and we do that first. We have to do that piece first, which is different than derivatives. Derivatives, we started with the multiplication, then did the subtraction. We have to do that entire process backwards, so we need to add first, then divide.
Is that weird thing in front just the S?
That's the integral symbol itself. That's how you know that we can apply the anti-power rule, because they're saying to take the integral with that symbol. Sorry, I almost just died there. If I didn't even write those instructions, that symbol would be those instructions, basically. So, then we move on to the next one. We have x to the first. So we do 1 plus 1, and then we divide. And again, hopefully we'll get to the point where we don't have to write it out in such great detail, but where it's our first time, I'm writing it out in great detail. Then the last one can be a little bit tricky. I have plus 1. What is my exponent on my variable here? If I put an x next to this 1,
0.
0. Okay, because x to the 0 is 1.
So it's 1 over 1 plus 0 times x.
So 0 plus 1, 1 over 0 plus 1, plus sign in between. Now I just do some simplification. We actually add and stuff. We would have 5 over 5, x to the 5th, minus 3 over 2 x squared plus 1 over 1 x to the first. Oh, what did I forget though? We should be writing this every time.
dx.
Nope, they had dx in the problem.
Plus C.
Plus
C.
c.
Oh, yeah.
That's very, very important. On the AP test, when we get to some integration problems, sometimes you get 1 full point on the free response sections for writing plus c. Yeah, and 1 point is actually a big difference on the AP test. So, it's very, very important. So we still have plus c. We could simplify a little further. Again, I'm doing the simplification in great, great detail. You can probably already see some spots where we could have skipped. 5 divided by 5 is 1. 3 divided by 2 doesn't simplify. 1 divided by 1 is 1. So eventually we want to get to the point where we can go from here to here without all these in-between steps. But it does take some practice, especially since all our practice so far has been differentiation, which is the entirely opposite process. So you're going to want to divide first when you should not. It's ingrained to multiply first, so now you're going to be like, hey, I should divide. But we have to add that 1 before we can divide. Otherwise, I would have divided by 4. 5/4, not the same as 1. So try this problem. The dx is just telling you that x is your variable.
Ask me that in about 3 weeks.
That's a good point. Okay, so you should have gotten x to the 4th minus 5/3 x cubed plus x squared minus 7x plus c. Now, I need to include an extra example problem. Then we're still going to do some example trig problems. But the only complications we could do with this is maybe we're given something where we could simplify first and then apply the power rule. So let's say we have example 1.5, because I already labeled the other one example 2. Let's say we have the integral of p times 3p squared minus 4p divided by, no, let's say plus something, plus 12 over p to the 3rd dp. And we could put parentheses around the entire thing. Sometimes they do, sometimes they don't. A lot of the books put parentheses around the entire thing, but not always on the AP test, so I don't always put parentheses. Just to say, this is where we start, this is where we finish, but it's kind of assumed that between the integral sign and dp is where we start and finish, So I need to simplify some stuff before I could apply the power rule. What could I simplify?
The P and then P.
Okay, the p and the p cubed could reduce. Then we would get 3p squared minus 4p plus 12 divided by p squared. Now what can I do? Because I can't integrate this because
Do you have
It's a
to
divide.
put the P squared to the top and put P?
you could do 2 options. You could bring p squared to the top and then distribute p to the negative 2 in. Or you could divide each of them by p squared. It depends on how you want to think of it. You could just divide each by p squared. Or you could write it as p to the negative 2. We won't have a fraction anymore. Times 3p squared minus 4p plus 12. and then we would have to distribute this in. So if we have p to the negative 2 times 3p squared, they cancel. So we would just have 3. We have p to the negative 2 times negative 4p.
So it'll be
What do we do with exponents when we're multiplying?
Add them.
Add them. Negative
so
2
it'll be p to the negative.
plus 1 is p to the negative 1. P to the negative 2 times 12, there's nothing to combine. So it's 12p to the negative 2. And we are going to run into an error that I forgot about, so we will show you. It should not happen on the homework because I used the program to generate it and not my brain. Okay. So
This is the perfect system.
integration here. What's the integral of 3?
3x.
3x or 3p. Remember, this is really p to the 0. So 0 plus 1 is 1. So we get p to the first divided by 1. So we really have 0 plus 1 here. We're dividing by 0 plus 1, so we get 3p to the first. Now this is the one where what we know so far will break down. What happens when we try to integrate this one?
It's 0.
It's 0.
Can't divide by 0.
And we cannot divide by 0. So there is a way to integrate it, but we don't know it yet. But you should not see any of them like this on the homework. So if we have p to the negative first, it's not going to work on the power rule. So this one doesn't work. This one we would add again p to the negative 1, divide by negative 1, so we get minus 12p to the negative 1. We're going to ignore the middle where I screwed up. So if we call our original function f of x, just like derivatives had a notation, if this original function is f of x, so not the integral but the inside stuff is f of x, when we get the antiderivative, we call that capital F of x. So capital is saying this is the antiderivative, where our apostrophes are saying this is the derivative. Okay, so we're going to practice some trig integrals, and then we'll get started on the homework. So we have 5 secant squared theta d theta. Now there's something that we've kind of been doing naturally, but we should talk about in detail. What am I going to do with that 5? I have a formula for secant squared. I don't have a formula for 5 secant squared. Okay, we treat it as a constant just like we treated constants when we were taking the derivative. Basically, I could take the constant outside of the integral.
Yes.
So now I know the formula for this. What's the formula for secant squared theta?
It's tangent theta.
Tangent theta. So we would have 5 tangent theta plus c. Why don't I have to put like tangent theta plus c in parentheses? Why don't I write it like this? What happens if we, well, this whole thing is tangent theta plus c. But what happens when we distribute 5 in? What's 5 times a constant?
5 by c.
Okay? But technically it would still be some constant, right? Since
Yeah.
it's still a constant, they kind of let c absorb any constant. Any multiplication or division into this constant, they say, well, that's still a constant. So they still call it c. So really, we don't have to worry about this. This was just to show you.
If you were to put parentheses, would the state be okay with that?
No,
No. Okay.
no. Okay, so one last try problem. So on the try problem, another thing we've been kind of doing naturally, it makes sense, is anytime I have a plus sign, I can take the two integrals separately. We've been doing that with our polynomials. We've been applying the anti-power rule piece by piece. Well, same thing here.
We're going.
Okay? I can really integrate these separately. And we don't have to write it out like this, but just to show you, I can take those integrals separately. Anytime I have a plus or minus sign, I can integrate those two things individually. Okay, so try this problem. So we have -3 secant x plus 6 sine x plus c. How could I check my answer?
Take the derivative.
Take the derivative of it and it would check your answer. If I took the derivative, we know the derivative of secant is secant tangent, and we just leave the constant there. Derivative of sine is cosine, and we just leave the constant there. What's the derivative of a constant all by itself?
0.
0. So this means we've checked out, we did our integral correctly. So if you're ever in doubt, differentiate it back to see